Good evening, people. Christopher Jackson here. I just wanted to actually record this video live today, but I had some bandwidth issues, and so without further ado, I was going to make a video about Lucie Green, or Professor Lucie Green, who is a Royal Society University Fellow, Research Fellow for UCL, and this was actually done at the Royal Institution, you know, where all the historic scientists have actually performed experiments, as opposed to just stood there and talked what seems to be a buzzword at the moment of pseudoscience. So pseudoscience is where, you know, perhaps you think of something or find something out and it becomes a fact, and other facts have backed up that fact. So without further ado, I shall start playing this video, and we can talk through it, and as good as it is. Now, I must say is that Professor Lucie Green is obviously she's a married lady. I'm sure she's a very nice person, etc., and she's done a lot of work, but all her presentation is based on information that she's got second hand. This isn't something she's gone out and actually retrieved herself. She has relied on information that's supplied to her from other bodies, whereas as you will find out, some of the actual historic scientists that she's actually referred to have actually gone out and made their own measurements and their own from their own experiments and from whatever equipment they were using. This was their own research. Now bear in mind, what she's doing is backing up this information with modern science, but her modern science is based on information that's supplied to her by a third party. Now that's very important when you think about it. So as much as research that she's done and everything, you know, I take my hat off to her, you know, it's no mean feat, but the way she presents out the information I have a major problem with, and that's the crux of this video, which is what I wanted to talk about on the live hangout. Now I wanted to do this live because it would give people an opportunity to question or say something in the chat. Perhaps there's something that I may have missed, and as opposed to actually recording this video and putting it out live, putting it out later, where people can actually ask in the comment section, as it were. So without further ado, I'm just going to play this video on, and certainly I do tend to have a humorous aspect of this, but I want to take this quite seriously, to be honest with you, because there are certain poignant parts in this, and it's about an hour long. I'm going to skip through some parts of it, but I really want to make a serious concerted effort to actually point out the deficiencies in supplying the information to people in the audience when really they have no idea what they're being told. So I will point out what they're being told. Okay, so I'll just start the video off.
Thank you. Yes, it is an absolute pleasure to be here tonight, and I've been wanting to come and give a talk at the RI for a long time, so this fulfills one of my ambitions in life, and I'm extra pleased to be able to come and talk about the book that I've been writing, 15 Million Degrees.
So she's promoting a book. Don't they all promote books when they do this show? The Royal Institution lectures. I have a book, everybody. Yes. Okay. Do you know, I might just go and buy this. I might go and buy this. But hey.
So I'm going to talk about the book tonight, which means
Yes.
you don't have to buy it if you don't want to. I'm going to tell you what's in it. Sorry, Penguin.
Penguin. I used to have Penguin books as a child, you know, detailing history and such, you know. I know there are publishers, so no.
But what I want to do is convey, first of all, where we are with modern solar physics research. What are some of the interesting topics that we're focusing on at the moment? But then make the most of the fact that we are here in this very significant building, and this spot is very significant for scientific developments and the publicity and the public engagement around science too. So when I was writing this talk, I thought, right, I must go and have a rummage through the RI archives.
A rummage through the RI archives. Um, it's not something that I could do, is it? I'm not going to be privy to that, am I? No. I mean, I'd love to do that. I'm not allowed, probably. Oh, I'm not a professor.
So I did that, and I spent half a day looking through Michael Faraday's work and many other people's work, reading the Friday evening discourses that have been...
Michael Faraday's work, but you have failed to mention anyone else. Faraday, keyword everybody. Everybody knows who Michael Faraday was, or thereabouts. Faraday's common name in terms of science and what have you.
Held here, and I would encourage you to do the same as well. You are all free and able to book an appointment and have a look through the archives, and it is an amazing thing to do.
Free to make an appointment and look through the archives. Yeah, I'll check that out. Thank you, Professor Lucie.
So some of the things I found out during that visit are in this talk. And I want to sort of convey a little bit about the history of science and then how we've got to where we are today and what that means for us in modern solar physics. So it's been a lot of fun writing this talk. It's been a lot of fun writing the book. But I also have an awful lot of fun doing the research too. And that's what I want to talk to you about really this evening. So when it comes to talking about the sun, I have to show photos, images that we take, particularly from spacecraft, and I always find it quite good to start off with these kind of images which show the sun as we see it in visible light. So this is how our eyes see the sun, the wavelength of light that our eyes detect. And actually this image is one that's been taken by NASA's Solar Dynamics Observatory. It's been in orbit now for just over 6 years, and it is the telescope or the suite of telescopes that give us the highest resolution images of the sun. So this is the visible light images. We see sunspots on the surface of the sun, which the number of which vary in time. So some of you may have heard about the solar cycle, where the number of sunspots rises and falls over a timescale of around 11 years. So this image, this is an old one now, actually from a few years ago.
Right.
And we've just come through solar maximum and we're on the declining phase of the cycle now. So we can look at the sun in visible light, see features on the visible surface, but I'm a space scientist. And so the view of the sun that I enjoy and that I use in my research is the view that we can only get by going above the Earth's atmosphere. And
only going above the Earth's atmosphere. So you're a sun scientist, a physics scientist, and the only view you can get is by going above the Earth's atmosphere. Well, what about this one? How about that one? Look, 2 sunspots with some other sunspots there. What about this one? Or what about this one? Or this one? Or this one? And let's go back to the beginning. This one. Did you notice the date on that, Professor Green? I took these pictures or photographs myself, not on a spacecraft. I took these from planet Earth or from the Earth with my P900 camera. I didn't need a spacecraft to have a look at sunspots. No, I took those myself with a 400 to 500 pound camera in my free time. There you go. But I digress. Oops, sorry, wrong one. I get back to here. Oh no, I've stopped it instead of paused it. I am a silly Billy. There we go. Let's carry on, shall we?
And that means we can see all of the sun's radiation, from radio wavelengths all the way through to gamma ray radiation as well.
Right.
But if we look in ultraviolet light, that's where I think we see some of the best views, some of the most attractive views of the sun. So if I was to show you the sun at exactly the same time as this image, but just using a different wavelength of light, it looks like this. Ah, excellent. I do love that response. I hope to...
Yes, this is apparently the whole wavelength of light. So conveniently, the ultraviolet light that comes from the sun is the higher end of the ultraviolet light gets blocked by our atmosphere. So we can't take these measurements from ground level because the atmosphere blasts out the the high frequency of the ultraviolet light, but the lower ultraviolet light they can see. But this particular one has to be done from space, so they need spacecraft to be able to view this picture. Can't do that from Earth.
To get perhaps one or two more oohs out of you as the talk goes on.
Yes.
So this is the sun's 1,000,000-degree atmosphere that we call the corona.
1,000,000 degrees, right? So 14 to go then. 1,000,000 degrees. I'm sorry, how did you measure 1,000,000 degrees?
You can see it has a completely different shape and structure to the photosphere that I showed you before with its dark sunspots. Now you see what looks much more three-dimensional, and that's because the light being given off from this layer, well, the light is coming from a layer that we call optically thin. So photons all through this gas can make it out and reach our telescopes. But what you're looking at here is light in the ultraviolet part of the spectrum, in the extreme ultraviolet part. So we can't detect this light from the surface of the Earth. We have to go into space. So we gather light across all of the wavelengths, but we don't just use the light to take images. I mean, my research focuses a lot on the images, but some of the instrumentation that we build at UCL uses the technique where you split the sun's light up into a rainbow. So in the sort of very basic sense, you might think about the prism, sunlight coming through a prism, perhaps as Newton did in the 1600s.
Yes.
The sunlight comes through, splits up into the rainbow.
Yes.
You could display that in a different way, and you could say, right, I'm going to have wavelength running along the horizontal axis, going from short wavelength blue light to long wavelength red light.
Right.
You could even plot a graph to show you how much light you have at different wavelengths. So,
right, okay, so first off, they've missed out indigo. Roy G. Biv, as I remember correctly. Richard of York gave battle in vain, I think it was. But this, as a scientific... So what's happened to indigo? I don't know. But have a look at this, because this again is quite intriguing. Now, they use this band here of the light spectrum. Now, let's remember, the visible light which is coming from the sun is what we see, what our eyes are designed for, is in the wavelength of 400 to 700 nanometers. Okay, that's the wavelength, right? So now what they're pictorially showing is actually can't see that here. Let's maybe just drop that down slightly. Bring it up. That's the wavelength on the x-axis. Okay, so and let's bring that to there. As you can see up here, you've got they've said, oh, we're just going to put the colours on the x-axis. Yeah, okay. So I have to assume what she's saying, that this is the intensity of the light here. And look, we get these dips, right? We get these dips here. Now, again, it's only a representation of what they want to do. I mean, that doesn't even line up with that. That doesn't line up with that. I know it's a bit crude and it's ready, but watch what she says about this. Or, sorry, listen to what she says about this. This is a top professor giving a Royal Institution lecture, and they give us cartoons like this. I'm sorry, this isn't science. It's a representation of what they want to tell you.
So this might look something like you have on the screen now.
It might look like something we got on screen now.
So this is a plot, just a sort of schematic showing that you might...
A sort of. It's science, people, a sort of. I'm getting annoyed. Sorry.
Have different amounts of light at different wavelengths or different colours. So what you're looking at here is something that we would call a continuum, which is a sort of curve. But then superimposed on that, you have what we call spectral lines. So in this case, dips in the amount of light, but they could also be spikes in the...
They could also be. So you're choosing what it is, right? Okay.
Amount of light. So we would say absorption lines or emission lines, depending on whether light is being absorbed by gas in the sun's atmosphere or emitted by gas in the sun's atmosphere. So I just want to sort of introduce this as a technique that we can use to learn more about the sun. looking at this particular part of sunlight, the visible light, gives us an idea of the surface temperature of the sun, which is around 6,000 Kelvin.
From light, okay, 6,000 Kelvin. The surface of the sun. I mean, come on. Yeah. How did you? With what did you measure the surface temperature of the sun? By the light.
But you can also use these spectral lines to probe what the sun is made of, because particular atoms of particular elements absorb and emit light at very distinct wavelengths or frequencies, depending on how you think about it. So these spectral lines can be really, really important.
Mm-hmm.
And one of the things that we do now is not just utilise the visible part of the spectrum, but also those other parts as well. So one of the instruments that we have in space at the moment that was developed by my department, the Mobile Space Science Laboratory, is flying on a Japanese mission called Faraday that was launched in 2006. And the kind of spectrum that this instrument takes looks like
A kind of. Be more specific, please.
this. So this is now the sun's ultraviolet light, taken using a technique where you just take a narrow part of the sun's disk. So it's like looking through some shutters. The light comes through the shutters, gets dispersed, so that you can see all the different wavelengths. So if I was to then turn this into a graphical representation, into a plot, we'd have wavelength going along that horizontal axis again, and then the amount of light at different wavelengths that you see. And you see that it corresponds, those bright streaks, where we've got lots of light coming in at that wavelength, correspond to a nice spike in the spectrum.
Right, so I this isn't very clear to me. Now, is this an accumulation of a picture of the light? So this speck here represents here. This bit here is brighter than there. Look, it's wider, but yet it has a lower peak. Have you shifted this on slightly? Look, that's brighter than there. Look, but yet it has a lower peak. Now, if this is sunlight, which we're actually recording through a slit or something, how is this one here any different to this one down here? Yet this is roughly about 285 angstroms. This is 275, 265 there. Not a lot with these little peaks and stuff. What does this actually represent? What? I've no idea. This doesn't. It just looks like you've got a lot of pictures together with different light coming through slits at every possible slit. How are you breaking this down to wavelength? It doesn't make sense.
So here we have a series of spectral lines, emission lines, each one being formed by light emitted by particular atoms or particular ions in the atmosphere of the sun. So I could label these, I forget exactly what they are now, but they might be ions of iron or calcium or silicon and so on. So we need more specifics, please. This is a lecture detailing scientific research and study. I don't want to hear the word or. All right? Tell me what it is. Don't say it's all this, it's all that, it's all this, Be more definitive, please. We can use them as a fingerprint to work out what's in the sun's atmosphere.
Right.
But because this instrument is something called an imaging spectrometer, we can do even more than that.
Imaging.
So I can take my slit of the instrument and move it slowly across the sun. And that means I can make images using my spectrometer.
Right, okay.
And I can make images
Here we go.
at different wavelengths.
Right.
And that's what you're seeing here. So these are images taken or created with our spectrometer on Faraday that show the sun's corona in different wavelengths of light.
Right, okay, so let's get my camera out of the way here. Now, different wavelengths of light. Now this picture up here, which is Fe12 at 195.1 angstroms. Now they're saying that they're using slitted camera effect for the light, but this looks like one continuous picture to me, doesn't it? And here also, all I have to do is get rid of the slits and I would have a complete picture. And here too, look, I have a plasma rejection here, which looks like complete. Why would I need to see that in different wavelengths to get that arc, or this one here? It's almost as if I'm looking through one of those Venetian blinds, isn't it? I don't need a Venetian blind to look at the sun to make up a picture, do I? Do I? No.
And those different wavelengths of light map to different plasma temperatures.
But they're all the same colour.
So going from the coolest in the sort of middle bottom to the hottest in the top left-hand side.
That one. They're the same colours.
One of the wavelengths that you see here is a particular emission line being given off by iron 12. You can see the Fe and then the numerals iron 12, 195 angstroms. And that's the wavelength of light that I use to make the picture for the front cover of the book. It's one of my favourite wavelengths of light that the sun gives off.
Excellent.
It's quite sad. We sort of develop favourites, and 195 iron 12 is my favourite.
Okay.
So, yeah. So I can gather spectra of the sun, I can make images, and I can also make movies. So I can run this over time. And you can see this particular region evolves. And actually this is a region of plasma above a sunspot region on the sun. But even more than that, so this image that you're seeing now has blue and red patches in it.
Oh no.
And so as well as using a spectrum to understand what elements are in the atmosphere of the sun.
Spit it out, girl, spit it out.
We can also look for things like plasma flows, because light becomes blue shifted when it moves towards you and red shifted when it moves away from you, the same as we experience with sound waves from a moving source.
Oh, right, okay. So let's talk about sound waves, shall we? How do sound waves travel? Sound waves need and require a medium to travel through, don't they? So light shifting from blue to red is not the same as sound, right? Now you need like a medium, for example, air, right? When sound waves are traveling, they're compressing and decompressing the air in front, right? So they travel out and so on and so on. In a denser medium such as water, sound can travel further because the medium is that much denser, so it has a better effect for the wave to ripple through the medium. Where there's a vacuum, you can't get sound because there's nothing to compress and expand the medium in front of it to propagate the wave. So when you're saying that light is similar to sound waves, it's not, is it? How can I look at the sun directly where I am from a fixed position and say these are blue waves now because it's it's building up and coming down, building up and coming down. You're so close to it with a fixed spacecraft, that's supposedly a fixed spacecraft. How can you talk about the Doppler effect? Surely this, I mean, again, it's licensed for information to just bamboozle people with saying, "By this is it." This is not true science. This is pseudoscience, really. You're taking information and cajoling it into a presentation to make you look more credible with the information that you have.
So having a spectrometer flying in space is incredibly versatile and allows us to do some really good physics about the atmosphere of the sun. But as I mentioned, I'm quite heavily reliant on images of the sun. And so I want to show you some of the activity that we detect once you start looking at a series of images put together. So if you go back to this view, this is the one I showed at the start of the sun's corona, looking at plasma that has a temperature of a few million Kelvin. And I can run a movie of this.
A movie?
But actually what I want to show you is a movie that's been made by processing the data in a particular way. So this is the start of the movie, and it's the sun at exactly the same time, but this movie, which has been made by one of my colleagues, Dave Long, is using the fact that if you subtract one image from another, so you literally take your intensity across the image from one image to the next and do a subtraction. So any features in the sun's atmosphere that become brighter will appear as white. Any features in the sun's atmosphere that become less bright will darken. And things that don't change will remain grey. Now this movie is slightly more complex because we've got 3 different wavelengths of light that we're using. So they're listed on the right hand side in blue, green and red. So we can do a little bit of a proxy about temperature changes in the atmosphere as well. But what I want to do is show you the movie, and hopefully you'll see dynamic activity revealed. So it flickers a bit as it's running before the main event happens, and you see a bright flash of light, and you see this huge eruption taking place in the sun's atmosphere. So this is a kind of activity,
a kind of. I hate that word, those words. A kind of.
Form of activity that we call a coronal mass ejection.
Coronal mass ejection. Now listen to the next few lines. This is great.
It's not the best phrase that we've ever come up with in solar physics,
Nope.
but it does what it says on the tin.
What tin is that then? God's tin? The tin of the sun? Does what it says on the tin? What sort of science is that? That's not even pseudoscience. Oh, really?
It is an ejection of mass of plasma from the sun's corona, from the atmosphere. And these are the form of, or this is the form of solar activity that I study in my research. Right. So later on, I'll come back to how we think these things are being formed. And
how we think. Now remember that. How we think they are being formed. We haven't derived at a solution to know how they are formed and give a representation of how they are formed. We think, and it leads on to them thinking about more stuff to come to an end solution, but to say how they are performed. But they're still based on an original thought of how they think these mass ejections are occurring, which is what I have a problem with.
Are incredible. We can watch them flowing out into the solar system. So this is now the same event, but seen using a different kind of telescope. This is an instrument that creates an artificial solar eclipse. So it places a disk in front of the sun, blocks out the bright light of the photosphere, and leaves the atmosphere of the sun revealed by light that's actually scattered by the plasma. So this isn't direct emission that you're seeing here, but scattered light coming from photons that are deflected in this cloud of moving plasma.
Okay, so photons in a moving field of plasma. The other thing as well, she does mention that this disk that's there, you've got this little stick that's holding it in place. Now, if I was to spend billions of dollars on a spacecraft and get it up there for one particular lens, I'd probably, miss out that middle part and blank it out. Why would I need a stick, something on a stick or something on a rod to put in there? Maybe they're using that lens for looking at other things where they don't need to blot out the sun. But hey, I didn't design it. But it's there, and she does say what that's there for and why it's there. It just seems pretty obvious to me why it is there, but why have it as that effect? Like a little lollipop sticking in its way.
So this coronal mass ejection flows away from the sun, and it travels. I forget the speed of this one, but in general they can move between.
Hang on, you forget the speed. You forget the speed of this one. I forget the speed of this one. I'm a professor. This is my life work. This is what I study day in, day out. Should come off the top of your head, woman. No, I forget what the speed of this one is. I can't remember. Get what?
Between maybe a few hundred kilometers
maybe.
a second to maybe over 2,000
maybe.
kilometers a second.
Maybe.
So they are fast.
Oh.
They carry the same mass as a mountain.
They carry the same. This is getting comical. They carry the same mass as a mountain in a coronal mass ejection. I like the way that coronal mass ejection, as if it has some sort of force, right? Now, okay, while I'm on the subject, I'd like. Okay, let me just bring up this picture. I could deal with pictures as well, Lucie. Let me bring up this one here. Right now, I have the electromagnetic spectrum here. All right, and if you notice down here, it says visible light, and this visible light is the light we get from the sun. right? You know, what you're studying, what your life work's about, okay? You know, solar activity and stuff. So, here we have radio waves, we have microwaves, infrared, ultravisible light, ultraviolet rays, X-rays and gamma rays. Now, we can't see the ultraviolet light with our naked eyes, and we can't even record ultraviolet light, the higher ultraviolet light to this end, with any earthbound instruments, because you need to be in space to actually see that, don't you? Right? Yes, as you've said previously. Now, with this visible light here, we can see these coronal mass ejections without, in certain, well, throughout all the wavelengths, whatever's contained in thereof, right? I don't want to sound too techy, right? Now, visible light, okay? Visible light, what we see, what's coming off, and you mentioned stuff. Now, the question I have is, at what point in the electromagnetic spectrum, now we all know, well, we should all know that an electromagnetic wave has an electrical field and a corresponding magnetic field, and as you will mention soon, polarization, depending which way it's run, right? Okay. Now, light waves coming from the sun are unpolarized because they're spinning. So the magnetic wave and the electric field are doing this, right? Doing this, coming, boom, right? Okay, that's the light from the electromagnetic spectrum. 400 to 700 nanometers, what we see, what our eyes are designed to see, as I said before. So at what point does that electromagnetic wave decide not to be a wave anymore and become a physical particle called a photon? That's what I don't understand. When does electromagnetic wave become a physical particle called a photon? You tell me that, because I don't understand that. How does it become a physical particle? Let's get back to the presentation, shall we?
So for those of you who remember your equations about kinetic energy,
mass of a mountain
squared, enormous amounts of energy, and it's been a big question in solar physics to try and understand where that energy comes from. So these are coronal mass ejections, and actually, incidentally, that black arm that you can see coming from the left-hand side of the image up towards the centre, that's the arm that holds the occulting disk in place in our telescope. And this is a telescope that's actually, this one's not orbiting the Earth. This one is orbiting a point called the first Lagrange point, which is a small fraction of the distance between the Sun and the Earth.
Perhaps I can interject here. Lucie, it's a Lagrange orbit. Is it the L1? Is it the L2? 1 million miles apparently from the Sun. Right? Okay. So there you go. Just thought I'd throw that in there. I've done my research.
So if I have this movie and I run it again, but this time allow it to run for longer, you'll be able to see another effect come into play. So first of all, you'll see the eruption itself. Off it goes.
Mass of a mountain,
and then
people.
As I run it further, you'll start to see these white flecks that appear in the image, and gradually a sort of snowstorm effect builds up. And it becomes completely dominant over the image to the point where you can barely see anything else. Now, these snowstorms
have travelled 92 million miles in a matter of seconds.
Are caused by electrically charged particles, protons, that are accelerated away from the Sun at speeds close to the speed of light.
Right.
They take, let me say how long the coronal mass ejection takes first of all. So I've already said that travels at 2,000 kilometres a second or more. And a coronal mass ejection takes perhaps 2 to 4 days. Perhaps. To travel the 150 million kilometres.
This millions of dollars have spent on this, and a camera looking at this thing and to turn around and say, "Oh, perhaps no, what? No, I need more definitive timescales regarding perhaps." If I were to write a paper on this and wrote in perhaps, they put a circle and red pen to say explain.
Kilometres between the Sun and us. These particles, these protons, that get accelerated during these events take maybe half an hour to get to us.
Maybe.
So they are incredibly fast. They hit our electronic detectors, they create a current, and that current is then registered by these bright specks. And actually these particle storms, we call them solar energetic particles, SEPs, again another not particularly romantic name, but does what it says on the tin. These are the kind of events that if they happen whilst astronauts are doing spacewalks, can be incredibly hazardous. The Apollo astronauts reported having flashes of light in their eyes even when they closed their eyes, and that was because of these high energy particles coming in and interacting with their retina.
Oh, so it was nothing to do with the Van Allen belts then. It's all this is to do with the this mountain of plasma that's been blasted out that takes no time to get to us.
But the more dangerous side is that if you get a storm of this ionizing radiation, you could end up with radiation sickness or leukemia, or perhaps even a fatal dose if it's really extreme. So the manned space program always looks at the sun to see what's happening so that they can forecast and get astronauts into a more shielded part of the space station should they need to.
It's ionized now as well. Ionization is where a particle is either given a net negative or a net positive. Well, let's just say it's charged. It's a charged particle. So it just throws that ionization in without a second thought, without any explanation at all.
So coronal mass ejections and solar energetic particles. I just want to show you another coronal mass ejection, which is my favourite one that the sun has ever produced.
Right.
And it's one that happened in June 2011. And I remember this clearly because I was at Cheltenham Science Festival at the time that these data were released.
Yeah, these data, yeah.
And I remember seeing the movie going around on the
movie. I remember seeing the movie.
Internet. And I didn't believe that it was real, actually. I thought someone had photoshopped it.
No, okay. Now, okay, I won't say anything. I'll just let it play.
So I went back to the NASA data archive. I got the data myself, and
she went back to the NASA archive because she thought the movie was photoshopped, or so she went to retrieve the data from NASA herself. Now, how did you get access to that data? Now, she got access to the data. Now, the data itself isn't a image file, it's information which is stored. So you retrieve that information. Now you have the information. Now you can, the raw data as such, if you like, depending on how the data is actually stored, digitally or what, right? So now you have that information. Now you can do with it what you will. So what do you do with it? Do you plot it on a graph? Do you make a picture? Or what? She's retrieved the data from NASA. This is second-hand data, don't forget. This is something that NASA has stored themselves from something that's supposedly up there. Okay? Just so as I make that point clear.
And this is the movie that I made.
So she made a movie, people. She made a movie from the data that she retrieved from NASA. And here's the movie. Not only is this look quite good, I'd be very happy if I made a movie like this from data. Now, what package did you use to crunch the data? It's absolutely fantastic. It's great.
You know, if you haven't seen this movie before, you might not think the sun looks particularly special on this day in June 2011. I didn't. But there's a region on here that just did something phenomenal. So let me play the movie. So off it goes.
Boom.
I got a little ooh there, yeah.
Yeah, you got ooh.
So this
Fireworks.
remains for me the most spectacular eruption that the sun has ever produced. This time, so much plasma was thrown up against the huge gravitational pull of the sun, 27 times what we experience at the surface of the Earth. So much gets thrown up that a lot of it falls back down to the surface of the sun. And I know of many PhD projects who have carried out research on just this one eruption.
Right.
So,
is that from retrieved data from NASA also? Did they retrieve the data? Or because you had the data, you just passed it on to them? Or are they doing their research from the movie that you made from the data that you retrieved from NASA, which is secondhand from supposedly from a satellite that's up there.
I have one student who's looking at it. So we want to understand what's driving these events. Where does the energy come from?
The sun. The sun, love.
So that's it, as shown in ultraviolet light, looking at plasma that's around 80,000 Kelvin. But I can also do what I did before and show you this so-called difference movie to see just how much more detail gets brought out when you use this technique. So this again is a movie by my colleague Dave Long, and this is the same event. It's much better, isn't it? It looks amazing. I trained as an artist before I trained.
Oh, hang on a sec. I'm just going to... I interjected there where I didn't mean to.
And show you this so-called difference movie to see just how much more detail gets brought out when you use this technique. So this again is a movie by my colleague Dave Long, and this is the same event. It's much better, isn't it?
Yes.
It looks amazing. I trained as an artist before I trained as a physicist, and actually...
I trained as an artist before I trained as a physicist. Trained people. Don't forget that. Trained. Now I'm just going to take a short break here. Now I'm going to pause this, but I'm going to leave the video where it is, and well, you won't notice, but I'm going to take it just a little break, and I shall be back. Right, so I'm back, and I'll just play this on.
I think there's something about these events that really appeals to me on an aesthetic level, that I just love to see these kind of data. So you can see this huge bubble that really rapidly expands, and then that material gets thrown up into the atmosphere of the sun. And these kind of difference movies are really useful to pick out the detail. Kind of.
I hate that expression. A kind of. You
can see the downflowing plasma. You can see where it's crashing into the lower atmosphere, which is just a gas. It's not a solid surface. But as the gas gets compressed, it gets heated, and then it starts to glow again.
Gas. It's a gas, people. It's a gas. Remember, it's a gas. Fusion ball of whatever. It's a gas. You know, I don't dispute that there's actually plasma plumes coming off of the sun, but I really dispute what they're saying. These, you know, I'll just play it on.
So coronal mass ejections are scientifically fascinating, but also pretty beautiful to look at too. But there's one more form of solar activity that we're focusing on in solar physics at the moment, and that's something called a solar flare. And I've got another movie here. This is now taken from one of the Stereo spacecraft, which is a NASA mission.
Right.
It's looking at the sun's atmosphere, again, the corona in extreme ultraviolet light. And when I play...
Something that we can't do, people. Remember that.
The movie this time, you'll see a flash of light happen in a region above the sunspots. So this is what we call a solar flare, and this is the form of solar activity that we've known about since 1859. A huge amount of work has gone into trying to explain again why these happen. When a solar flare occurs, you see a flash of light across the entire electromagnetic spectrum, from radio often into gamma rays, but certainly this intense brightening in ultraviolet light, and also in X-rays as well.
Now, just stop and look here at the picture which you're actually looking at. Let me get this out of the way here. They've got the sun here. Now, if you didn't know it, like looking at this in 2D, it just looks like a whatever. But they actually move it to give it the perspective of a 3D effect, you know, and to all intents and purposes, they're making it look like a ball as well, aren't they? You know. So just to point that out, you know, why would they show this on this as a side elevation? I'd want to be looking at this face on, surely, to have a look at the effects across the sun, but no. You only get a partial glimpse from here. All right. So subconsciously, you're thinking that this is a ball, right? You're thinking of it as a ball right now, aren't you? I know you are. Yes. Let's play it on. So
solar flares are another big topic of study. This is another movie taken from the Soho spacecraft.
Oh, okay, all right.
Just showing what a solar flare can look like when it's directly along the Sun-Earth line. So in this case, sort of top middle of the sun, you see a solar flare go off. There's also a coronal mass ejection from exactly the same region at exactly the same time.
Right.
But it's just hard to detect in these images. You need those artificial solar eclipse images to see it.
Right.
And you have a solar energetic particle event.
And
So we have coronal mass ejections, energetic particles and flares happening often all at the same time.
wow. So it took. So we have to assume that this spacecraft took the picture at 92 million miles away, because it's in a Lagrange orbit, which is, a million miles away from the Earth, apparently. And before we knew it, all went fuzzy. So it's like, it takes 8 minutes, apparently, for these sun's light to reach Earth. But that plasma and that flare ejection, boom, was there in seconds. Seconds! Not even that. Not even that. But I digress.
But perhaps one of the biggest discoveries about the space age has been to do with our relationship with the sun. And that's well illustrated by this animation.
It's an
This
animation.
takes a bit of a setup, because what you're seeing here
It's an animation.
are images from 2 different spacecraft. And again, this is the NASA's stereo mission. You'll see I've pointed to the sun in the centre.
Yes.
So now the sun looks tiny. This is such a wide field of view that we're looking at.
You got
The
your
sun's
lollipop in
absolutely
there.
tiny.
Yes, right.
On the left-hand side of that image, you've got the view from one spacecraft, which has left the Earth, travelled away from us, and is now looking back along the Sun-Earth line. On the right-hand side, you've got the counterpart spacecraft, which has left the Earth, gone behind us in our orbit around the sun.
At exactly the same distance, people. At exactly the same distance. Can you believe this? I mean, come on. It's an animation. I'd love to see the data for this. But, again, I'm just going to play this on, because I'm currently at 46 minutes in this video, and I'm only about a third of the way through this. It's ridiculous. I can just spend 3 hours just talking about this, but I don't want to waste any more time. Here they talk about the effects of the ejections. That's the CMEs, electricity network interruptions, possibility of cascading failures, satellite surface charging. Satellite surface charging. Well, how do they discharge it then? GNSS errors, flares. They've got atmospheric heating, ionospheric changes, HF communication problems. That's because HF communication apparently use the ionosphere to retract the radio waves back to the ground. Energetic particle releases, is that what it is? Energetic particles. Ionizing radiation at aircraft altitudes damage the spacecraft and aircraft electronics. Well, I don't know for 1 minute of any aircraft falling out of the sky because of a CME. And again, HF communication problems. And it just, honestly, so they need to research this so they can improve systems. It's a wonder any satellites have stayed up there at all and still been able to communicate, because we have all these CMEs, flares, ejections, and energetic particles flying around. Let's carry on. She's got her arms up here. Let's see what she starts saying. Sorry.
Metal umbrella tomorrow as well.
Oh.
So there's a huge amount of...
So she's talking about these particles, and
so myself, my colleagues and scientists around the UK are all working on trying to understand what does this solar activity mean for our everyday lives. And very recently, the Met Office set up a space weather forecasting centre.
Right.
So you can go to the Met Office to know whether you need your umbrella tomorrow, and Tim Peake can go to know whether he needs his, metal umbrella tomorrow as well.
Tim Peake. She got Tim Peake in it. There you go. Tim Peake. Bless you.
So there's a huge amount of investment, but for very good reason. So that was my kind of intro section to show
Kind of intro section.
some of the solar phenomena that we're focusing on to try and understand. And I'm going to come back to why or how we interpret them, what the physical processes are, in the last part of my talk. But for the middle part, I want to just say a few words about how far we've come. What has the story been to get to the point of being able to understand these events? And we have...
What has the story been? I would say, where has the research begun and led us to? No, it's not a story, is it? Is it a story? Is this talking about a story?
I've made a huge amount of progress.
Huge
So I was
amount.
sort of reflecting on, okay, I'm giving the talk here tonight at the RI. What's been that story since the RI was formed in 1799? And I think it's fair to say that we had fairly primitive views at that point. Now, the images that I'm showing here predate the formation of the RI. So on the left-hand side, I've got a drawing of the sun made by Thomas Harriot in 1610. This is the first drawing of the sun through a telescope, or the first drawing of sunspots even.
Okay, so she's going on about historically about who drew what, and she's talking about different scientists. I'm just going to forward this on. Yeah, she mentions this chap
at the
here.
end of the 1700s, and he was the person
Herschel.
who had the best telescopes. And
He had the best telescopes because his family were wealthy. His father, what's the word I'm looking for? His father actually.
would they see? And so would they see? And
Well, his father accommodated him with his, spoiled him with his obsession with this. So he had the best observatories, from a wealthy family, and 9 times out of 10, it's in history, people who come from wealthy families have the time and the resources to be able to do the research, but come up with what they state is the matter of science, and so. Who's to argue with that? Because nobody else can repeat the measurements because they're not privy to having the equipment. So people look at this chap and think, wow, he's really clever because he has the equipment. No, you can't touch it. It's just for me. I'm looking at it and I decide what I think is the best guess for what's happening. So, So we'll move on with that a little bit. And she talks about she'll talk about that. She talks about referencing a book. Oh, and it goes into magnetism. All right, no, I'll just see where she starts off with here. This is Herschel. Yeah. See what you can say
on
here.
the sun, and he ended up concluding that a sort of planetary interpretation of the sun, where you have a glowing atmosphere, and the sunspots are these holes in the atmosphere, breaks in the hot glowing clouds where you can see down to the surface of the sun. The cool surface
Talking
of
about
the sun.
sunspots. Yeah.
And in his paper of 1795, he even has this line where he says, "This leads us on to suppose that it is most probably inhabited, the sun, like the rest of the planets." Lewis, is that true? By beings whose organs are adapted to the peculiar circumstances of that vast globe.
Now, how familiar does that sound? Leads us on to suppose that it is most probably inhabited, like the rest of the planets, by beings whose organs are adapted to the particular circumstances of that vast globe. Okay? Alright? No wonder you wanted to get this in. Probably, suppose, supposedly, globe. Key words there, right?
So I think this says everything, that we really didn't
It does, doesn't it?
have a clue.
No, exactly.
But today we do. So how did we get there?
Right.
And that brings me on to the Royal Institution and the key player of the Royal Institution, which is Michael Faraday. Because what I want to talk about now is magnetic fields.
Here we go.
It turns out that magnetic fields are centrally important to understanding the sun.
Right, so okay, so I'm not saying the sun doesn't have a magnetic field, but I have problems with the temperatures they say. So for ferromagnetic material, there's a Curie temperature that materials lose their magnetism at a certain temperature. So, but if the sun is not made of any particular type of material, then it won't be subjected to the Curie law. So if I have a body up there that's emitting light and plasma, um, I really don't know what's causing the plasma ejections. So I try need to understand, and why do I have these black holes there? So it just goes to show that Herschel and all those people that were looking at the sunspots all those years ago, 300 years ago, with all the spacecraft that they have up there at the moment, they're trying. It's the best guess of what's happening, and the way they try and explain it is by magnetic fields, charged particles, and so on and so on. And this is what she's leading into. Now, if I have hot porridge, right, it's bubbling away in the pan, and I get like a moisture bubble in there. It comes to the surface and it bloops out, doesn't it? But I have a heat source which is at the bottom, causing that expansion to come up to the surface and blow out. Right. So if I took a high-speed camera shot of porridge, okay, or ready break, depends how you make it in the pan. It's like it would bloop like this. You can look at mud flats, with these hot springs with mud flats in them. If you look at the way the actual mud blasts out, because it's got some steam inside there, some water effect within a dense material. It wants to come to the surface and release. Yeah. If you were to look at that in slow motion, it would look similar to the type of plasma ejections you get in with the sun. But what they're going to start saying now is that it's to do with magnetic currents magnetic fields, and it releases the energy. And they talk about electrons, and it's just they're making stuff up to make it fit what they're looking at. They don't really know what's actually happening. They have no more idea than Herschel did way back in the time, or Newton when he started looking at the sunlight. And that's true. That's the truth.
And so that's what I'm going to focus on for the rest of my talk. So when I came here and I had a rummage through the archives, of course I wanted to see the work of Michael Faraday. And
who doesn't?
Charlotte New here very kindly showed me Michael Faraday's lab book. So this is one of them. This is his writing. And in this experiment, he's using a wire that he's passing a current through, and that's generating a magnetic field. So this is Ampere's law. Pass the current through the wire, and you have the circular magnetic field around your wire. But what I hadn't realised was how he had captured that magnetic field. And that's what's being shown here. So these are iron filings that he put down onto melted wax, so the wax would set, and in it would be captured the shapes and the strengths of the magnetic fields. Amazingly simple. Again, something that we could all in this room do. I just love the fact that this is so important, but so simple. And this is another one of the images or figures.
But that's magnets on Earth, love. It's magnets on Earth. It's not to do with the sun. But it's amazing how they take this. She said it's amazing. Yes, amazing how they take this and make a comparison to what's happening on the surface of the sun.
That he created. So again, you can literally see where the magnets were underneath the paper, and you can see the shapes in the iron filing. So this is classic school experiments investigating magnetic fields. At home, I have a pot of iron filings. It's so good. And so here you can see the shapes in the magnetic fields. And one of the things that I didn't realise for a long time is that when I talk about magnetic fields and I'm trying to convey them to a colleague, what I quite often do is draw a picture. So I would draw my magnet, my North Pole and my South Pole, and I would...
Yeah, drivel, yeah, okay, it's a school thing, all right, okay, let's carry on. Oh yeah, she talks about a chap called Zeeman and the work he did. She's trying to fit everything together now with... let's just pull it to here. I think there's something more up here.
Example, you might have a stationary component at the original wavelength and then a component either side, one at a slightly shorter and one at a slightly longer wavelength. And this is now called the Zeeman effect after Zeeman. And it's an amazing piece of research because it means we can detect magnetic fields from a distance. If something that's emitting light is also magnetized.
All right, perhaps I should bring that back slightly because it...
One of the other things he was working towards was to use a spectroscope. So as I mentioned earlier, we use spectroscopes or spectrometers today to split light into its component colours and look at the spectral lines.
Yep.
And Michael Faraday was interested in, would there be any effect on a spectral line of a substance, of an emitting substance, if it were influenced by a magnetic field?
If it were, not that it was, if it were. So she's setting up the groundwork now to say that it's to do with magnetism, right? Here we go.
Now, his apparatus wasn't good enough to answer that question, but it's something that got picked up again or continued to be worked on. And so my story now moves from Michael Faraday to some other people who were key players in bringing us from magnetic fields in the lab to magnetic fields, well, on the sun. So the next person in the story, which is heavily condensed, is Peter Zeeman. Mm-hmm. And he was also working on spectral lines and magnetic fields. And he was the person who showed that, yes, if you had an object emitting light that was a magnetized gas, for example.
How do you know it's magnetized? For example, right? How do you know it was magnetized? Spit it out, love.
That would be affecting the spectral lines. So earlier on I showed these peaks where we had one spectral line per element or per atomic transition. But what happens when you have a magnetic field is that the spectral line splits. So it can broaden, and in a strong field it can split. So for example, you might have a stationary component at the original wavelength and then a component either side, one at a slightly shorter and one at a slightly longer wavelength. And this is now called the Zeeman effect, after Zeeman. Right. And it's an amazing piece of research because it means we can detect magnetic fields from a distance. If something that's emitting light is also magnetized, there's a fingerprint of that in the light that it transmits to us.
So how is light magnetized? Light is an electromagnetic wave. It has a component of magnetism and a component of an electric field. It's not magnetized. Is it charged or is it magnetized? It's not magnetized with respect to what? It's where it's leaving or where it's going to. It doesn't have. It must have then a complete magnetic field in itself, surely. The hands, perhaps. Oh.
So that's the first piece of information. So I'm building now towards something that we learned about the sun. The second piece of information that actually was announced right here in 1897 by J.J. Thomson, who I've shown here, is the discovery of the electron, although it wasn't called the electron at the time. But subatomic negatively charged particles.
It wasn't called the electron at the time. What was it called then? Tell us. What did he call it? Subatomic negatively charged particles. Negatively charged with respect to what? With respect to what? At any given point in time. Right? Nothing is negatively charged. Nothing can have a net negative charge. It's in a state of charge going from one aspect to another, going from a charge going towards zero. That is a state of negativity. It's not a net negative charge. Nothing maintains a net negative charge in this universe whatsoever.
So that's the next piece of information that I want us to keep in mind.
Keep in mind, people. Keep in mind.
Third piece of information is an experiment that was carried out by Henry Rowland. He did an experiment where he had an electrically charged disc and he rotated it and realised that it created a magnetic field. So here again we've got this link between electricity and magnetism.
very loosely, I have to admit, very, very loosely, a disk that's what, electrically charged with what? Electrostatic or electric current? I mean, it's loosely connection. So,
flow of electrically charged particles, and so on. So these three pieces of research come together to be relevant to our story of the sun because they were put together by this man. And this is George Ellery Hale. Maybe I could just have a show of hands if you've heard of George Ellery Hale before. Oh, yes, some people. Brilliant. I think he is the most important person in solar physics. I'm so glad that he's a name that's familiar to some people in here. If he's not, by the end of tonight, he will be. He'll be someone that you'll be thinking about. Mm-hmm. He was an amazing American astronomer / engineer. He came from a wealthy family. He had a very high quality observatory even as a child that his father funded for him.
Yep.
But he had an amazing mind.
Yep, he did. And he goes on to show, let's see what she says here.
Call it hydrogen alpha, and it's a really important line for observing the sun even today. And this is the image that he created.
Looks like
this is now
looks
looking
like a sphere, doesn't
not
it?
at the photosphere of the sun, not at that visible surface, also not at the corona high up, but at a layer in the middle that we call the chromosphere. And you see a huge amount of structure. You can probably just about see some sunspots on the top right and one down right in the centre in the bottom. Mm-hmm. And then also this snake-like feature that we call a filament in the sun's atmosphere. And Hale noticed something curious about the shapes in the sun's plasma. So he knew by this time that the sun was hot gas. So the element...
He knew that the sun at this time was hot gas. A guy that was stuck on Earth, looking through telescopes and whatever time, she just throws that out there. He knew that it was hot and hot gas. He knew that. Really? I mean, it's almost as if you're taking something from the future and bringing it back, saying, presuming that's what he knew. Honestly, this is just a license to say what you like. That's not science, is it? And then you're looking at these vortices here. You go on to say about the vortices. Come on. Rubbish. Now, I'm going to have to look at this one here, bring it forward to here.
An image now to illustrate something
that
caught Hale's eye.
Yeah.
So this is...
Now, let's have a look at this now. What they're showing here, again, it's from a spacecraft. And look what they do here. Is this necessary to actually put these lines on the sun to give it the effect that it looks like a bulging ball, right? Now, they chose to put these lines on, right? It just tries to make it look as though it's a ball, doesn't it? When you have those geometric lines on there, it's rubbish. I take offence at that.
A modern image of the sun taken in the light of hydrogen alpha. This is actually an image taken back in April this year. So April this year, when we had an enormous sunspot crossing the surface of the sun. And I don't know if anyone in this room went out and saw it.
No,
yes,
you
saw it.
Yeah.
Did you have eclipse viewers? Brilliant. Have you got that photo with you? Oh, I see it later. That'd be brilliant. So this is an amazing event. So we get so excited. Large sunspot appeared on the sun, and it was visible to the naked eye if you had filters. So we all went outside and put on our eclipse viewers and looked at this sunspot. It was amazing. And it was interesting. So I had a new PhD student at the time, and he was saying, I can't see it. I was like, right, I need to train you a bit more. So next time this happens, he will be able to see it.
I need to train him a bit more to actually, tell him what he needs to look at so he knows.
So this is the sun in hydrogen alpha. This is the visible light image just to show you that sunspot. It's absolutely ginormous.
Yeah.
For size, as a context, you'd fit 110 Earths across the width of the sun.
So she had to get that in as well. This is, the size of the Earth compared to the sun. It's 110. All right, 109, 110. That's what they say. Okay, but throw that in there as well, right?
Is many times the size of the Earth. This sunspot, absolutely enormous.
Yeah.
But this is the at the same time in the light of hydrogen alpha, just picking out a narrow spectral range.
Mm-hmm.
And then if I zoom into that sunspot region, hopefully what you'll see is that you've got the dark
Hopefully.
sunspot, but you've got these sort of spiral, like Catherine wheel sort of features around the sunspots. And Hale called these solar vortices. So he was looking at the sun thinking, okay, there's probably electrons here.
Okay, probably electrons here. There's probably what? How would you deduce that there's probably electrons there looking at a vortice? Huh? What? There's probably electrons there. No, think about that. See, probably. Now she's saying that's what he would have thought. Somebody's been dead for 200 years or 100 years or whatever, you know. He probably thought that. But it doesn't matter because we've got our grid lines here on the ball, here on the ball's sun, look. Makes it look round, doesn't it? It's amazing.
There's some sort of vortical motion, and
Some sort of.
vortical motion of something charged can create a magnetic field.
If something charged create a magnetic field.
And if it creates a magnetic field, I know how to detect it because of the Zeeman effect of splitting of the spectral lines.
There you are. She's backing up her science with pseudoscience. It's not a true given fact, is it? Even with these spacecrafts up there.
And he knew how to test that because he was an amazing instrument maker.
He was an amazing instrument maker. Well, would you like to actually enlighten us, no pun intended, with regards to what instruments it was he used?
And so in 1908, George Ellery Hale became the person who had put all this information together, built the right telescope, looked at sunspot regions and detected that they were indeed sources of strong magnetic field.
End of story, people. That's it. In 1908, magnetic fields, that's it, right? Okay, you got it? Right, you better believe it.
So the first discovery of a magnetic field beyond the Earth, and I would say the point when solar physics really began. So 300 years after the first telescopic observations of sunspots, we finally knew they are sources of strong magnetic field.
I would still question that. I really, really, really would. I mean, to get a magnetic field, you have to have some sort of but they're talking about electrons, you know. So electrons and changing this will create a magnetic field. But at the temperature they're saying, I mean, it goes way beyond the magnetic effect. I'm not saying the sun doesn't have a magnetic field. It probably does, but at those temperatures, really?
So when we look at images like this today, we know that they're magnetic field regions, and they're regions where plasma, electrically charged gas, is trapped and is able to cool down slightly.
Slightly is able to cool down slightly. Why is it able to cool down slightly, Mrs. Green? Please enlighten us. Why it's able to cool down slightly? Just by stating a fact proves nothing.
Relative to the surrounding photosphere. So the magnetic field and the strength of it is what creates these dark spots on the surface of the sun. And this discovery was so important. And it found an advocate here at the RI in Arthur Eddington, who was a mathematician and astronomer and very famous scientist working at Cambridge.
So, famous astronomer, scientist, working at Cambridge. Here comes the money sentence.
He was the person who also supported Einstein's general theory of relativity.
He was also the person who supported Einstein's general theory of relativity. Well, there you go, people. You know, he's backing up pseudoscience with pseudoscience. You know, it's the buzzword at the moment. But it's true.
Went on an eclipse expedition in 1919.
He didn't have a full-time job then, did he? He was all right.
To measure deflection of starlight during a solar eclipse and looked at or backed up the idea, backed up Einstein's theories. But anyway, that's
another story, isn't it? Yeah, you just skip by that. Yeah, nothing. I can't really explain that. I'll just carry on.
The story. So in 1909, Eddington was giving a Friday evening discourse, and he was supposed to be talking about, or was talking about, the moons of Saturn.
Supposed to be.
How many have been discovered? I forget, it's a tiny number compared to the, 60 odd or whatever it is we know today. So he was talking about the moons of Saturn and comets. But I love the fact that he ends his Friday evening discourse, and again, these are all here in the archive. Some of the...
It's true because it's written down. I'm just going to skip this because it's nothing here. It's just there. What I want to get onto now is get away from that. She goes back to these.
It's not only a very dynamic ball of plasma, but it's a magnetized ball of plasma.
There you go.
And so that's how I want to finish off in the last section of my talk, the last few slides. So my job today heavily revolves around measuring and using magnetic field data of the sun. So the kind of images that I would use are like this. This is now a magnetic map of the surface of the sun.
Based on their beliefs of what people have said before. Okay? Right? This is supposed to be a spacecraft now. So now that what they're doing is they're mapping the sun based on what they believe are magnetic fields. When it's just it could be intensity of the light surrounding, but it's derived by magnetism apparently. I hope you've learnt that already.
It shows us regions where the magnetic field points out of the visible surface, and that's shown in white. Right. Then regions where it points in black. So that's like having a north and south pole on the surface of the sun.
But in many places.
And there will be magnetic field going from one pole to the other. Now, of course, I can't get to the sun and sprinkle my iron filings, but what I can do is make use of this data, the strength and direction of the magnetic field, and then the physics of magnetic fields to create what we would call an extrapolation, illustrated here using the concept of magnetic field lines as introduced by Michael Faraday.
Okay, right. Now this is like a license to actually draw lines from points on the sun. This is actually, they've drawn this in themselves. This isn't exactly what's happening. They can't measure this. There's no way they can measure this. Absolutely no way. They're trying to deduce this is what the magnetic field is. Alright? From vortices on the surface of what they're saying is the sun, they're writing this in. Because when they've looked at coronal mass ejections, the coronal mass ejections are doing this, the same as what hot porridge does when it boils, right? It's bloop, bloop. How do we know what the sun's made of? They're saying it's a gaseous ball, really, a fusion, right? I mean, these lines have just been drawn in ad hocly, you know, to try and fit the fact that it's these large magnetic fields. They really don't have any idea at all. And they put numbers on.
So here you can see between the black and the white giant arches of magnetic field.
I can see them,
stretching out far into the atmosphere of the sun.
Right.
So you cannot study the sun without thinking about or knowing and studying its magnetic fields.
You can't study the sun without thinking or knowing there's magnetic fields. Just to re-embed the fact that the magnetic fields are there.
And as those sunspots change over time with new ones forming, old ones dying, so the magnetic field in the atmosphere of the sun and threading the surface evolves. It is a dynamic object.
Well, I don't dispute that it isn't a dynamic object. I mean, the fact is that when there are no sunspots, and I have pictures myself that I've taken with no sunspots, what's the sun doing? It's still emitting its radiation, isn't it? So I perhaps would think that sunspots are an anomaly. It's not how the sun works, you know. They're not required as such. I think it's just a little bit of a glitch, perhaps. What I'm gleaning from this is that you really don't know how the sun works at all. You're just trying to come up with the best guess as to why sunspots are black. Really.
But once we knew about magnetic fields,
Oh, we know now. We do. We knew. Once we knew about magnetic fields, which is a whole lot of conjecture, if I may say so,
could start to understand the forms of solar activity. So the solar flares that I mentioned are interpreted as being releases of energy stored in magnetic fields in the sun's atmosphere.
Okay, so what causes that energy to be released? What's the point where it says, I'm going to give up now, poof, away I go? You know now. Really? This isn't science. This is just the best guess. It was just complete fabrication.
Releases of magnetic energy, an energy that's then converted into other forms.
By what? It's converted into other forms. By what? Energy conversion from one form to another that has to have something acting upon it to actually happen. What is that? You don't say that. You're just loosely stating facts. It's rubbish. Sorry.
Acceleration and radiation. But for the form of activity that I'm most interested in, which are these coronal mass ejections,
the size of a mountain,
I want to show you that in a bit more detail.
Here we go.
So this is an illustration of one quite small coronal mass ejection that happened on the sun.
Well, she talks here
on
about
the top left-hand side,
twisting vortices. It's boring. It's not. It has no relevance in it. She's just re-embedding her research into. Oh, there is one point where she says...
data, so this is artificial eclipse. It's not a particularly clear movie, but you can see that material being ejected away from the sun. But we wanted to understand, we do want to understand, and this is a worldwide effort, why does the sun suddenly erupt the mass of a mountain into the solar system at speeds of up to a few thousand kilometres a second? And in the same way that we think the energy that powers solar flares comes from the magnetic field, we also think that for these coronal mass ejections. That the sun's magnetic field is dynamic, it evolves, and it stores up free energy. But that's not enough. And a lot of the focus in recent years on understanding coronal mass ejections has been around what shapes the magnetic field takes on. So what I want to show you now is a series of images of this little region of magnetic field and plasma, and how it changes over a couple of days.
That's the vortices she's talking about. I really want to get to what she says at the end here. It's got 1 hour 22. This is unbelievable. I'm sorry, folks, if it's gone on too much. Get to the end here. Let's talk about this. Here we are. Back to the black spots. So sunspots. Here we go.
Okay, I think I've probably filled my time, so I just have one last slide.
Now I'm going to stop this here. Now, bearing in mind everything that's gone before, right? They talk about spacecraft and being Lagrange orbit and looking at the sun. And here's a view of the sun here with the sunspots on it. Looks wow, all that spacecraft is up there doing stuff. But look at the background, people. Stars. Look, yes. Look, I can see stars. Wow, they're brighter than the sun. So again, they must have put this backdrop in, because every time from Earth, I take it through my filters of the camera, and I can't see stars not like this. This is amazing. Look, I can see stars behind the sun. Wow, how real is this picture, people? Ask yourself that.
Finish the talk without at least mentioning that, okay, we can look at the visible surface of the sun, we can look at the atmosphere of the sun, we can look at the atmosphere out towards the Earth and beyond, but we can also look inside the sun.
Can you?
So this last visualization makes use of the fact that we can probe the solar interior.
Probe the solar interior. Here we go, people. This is the actual crux of it. This is like gold dust, really. How would you have the audacity to stand in the Royal Institution and say probe the interior of the sun? With what? With what? Where Faraday created his experiments and showed them, and you have nothing but slideshows and movies and conjecture and twisting what people have said in the past. Honestly,
where the fusion is happening to generate sunlight in the first place.
Yeah,
and
fusion.
also where the magnetic field of the sun is originating. So is this...
What causes a magnetic field? All right. What causes what has to happen to have a magnetic field? All right. I either have to have a solid mass of ferromagnetic material, which has a magnetic field embedded, and which is naturally occurring, right? Which even in this environment nobody can explain, right? But I heat that ferromagnetic material up to the Curie temperature and beyond, and it ceases to be magnetic. So now I have a body that's floating in free space, which now has these magnetic fields. What's the magnetic field being driven by? And she's going to try and explain this now.
Movie plays, you'll see the sun spinning, and then it will open up and show us the inside of the sun.
Here we go.
We use the technique of helioseismology to probe inside.
Helioseismology. That's a new one on me. Now look at this, people. Come on. It is a movie, right? It's just a cartoon of what they think is happening to back up what they're trying, or what Mrs. Green's saying, right? Okay, here we go.
It's a technique of using sound waves.
It's a technique of using sound waves. This is just getting better. It's a technique of using sound waves to probe the sun. I mean, sound does not travel in a vacuum. We all know that. If you remember the bell jar experiment from school, you have a bell jar that's evacuated with a bell inside which is ringing, and as it's ringing and you evacuate the chamber, the volume just goes to nothing. But yet light waves still penetrate through the vacuum, so you can see the light waves, but they're talking about light seismology here. But she said it. I'm going to repeat it. Here she goes. She says it.
Also where the magnetic field of the sun is originating.
Mm-hmm.
So as this movie plays, you'll see the sun spinning, and then it will open up and show us the inside of the sun. We use the technique of helioseismology to probe inside. It's a technique of using sound waves measured at the surface of the sun to...
Measured at the... Now remember that, measured at the surface of the sun. I don't know of any spacecraft that has been able to actually go to the surface of the sun. I mean... Oh, come on, people. This is a mainstream professor lecturing at the Royal Institution. I'm not going to say about Faraday turning in his grave or whatever, but it's complete garbage. It really is. This culmination in her presentation is completely farcical. It is just... I can't describe how disappointed I was with the ending of this lecture. It really was disappointing. But I'm not surprised.
Look inside. The sound waves pass through the sun, pick up information about the interior layers, and then we collect it at the surface. So this is a NASA visualization that shows the outer layers of the sun. And all the lines you can see are magnetic field lines.
Are magnetic field lines. So they're just telling us they are, right? They're not saying it's what they found. They're telling us that's what they are. Really?
and you'll see that they
You'll see.
evolve over time. They become tightly packed together and then they die away, and then they become tightly packed together and they die away. On the right hand side you can also see the number of sunspots varying over time. In blue and red you have the interior flows being indicated, and then on the left hand side the blue and yellow is the strength of the magnetic field inside the sun. So we see sunspots at the surface, but they begin their life as magnetic fields that get amplified inside the sun. Incredible. And actually, the origin of...
They originate inside the sun, right? So how do they get amplified? I don't know how to amplify a magnetic field. I really don't. In all the years of my electrical and electronic experience, how do I amplify a magnetic field? The only way I can amplify a magnetic field would be to pass it through a transformer, perhaps, to create with more turns, right? So you're saying that it originates in the center of the sun, and as it comes through the sun, it gets amplified. I'm really just like terribly disappointed with this. If I was there, I'd be sticking my hand up every 2 minutes, in the question answer session. I wanted to get through the question answer session, but I don't want to do that. I might do that on another video. So here we go.
This work that we call the solar dynamo, the transformation of rotational energy of the sun into magnetic energy, that was carried out at Mount Wilson, which is one of the observatories that George Ellery Hale was absolutely key in. So many things track back to Hale.
Yes.
So I think I should probably finish on that point, but I want to say I hope that's given you a flavour of the amount of time it's taken to come to understand something as simple as a sunspot, several hundred years.
But you're concluding as if you now understand it based on beliefs and observations which haven't been backed up.
But that our modern view of the sun is that it's dynamic, it's variable, but it also has an impact on us here on the Earth. So I think I would say thank you for listening, and I can take any questions.
Well, that's it, people. I wanted to do the question answer session as well, but I mean, this has gone on for like an hour and a half. It's unbelievable. A 54-minute presentation by Professor Lucie Green, and I hope you enjoyed this, but I hope you're not as cheesed off as I am with it, because it really is just complete nonsense. It's not even a best guess. It's not science. So I'll leave it at that. And if I can be asked, I will do the question answer session that she gives after this in a separate video, because she doesn't half waffle on, Okay. Thank you. Goodbye.